A History of Classical Physics from Antiquity to the Quantum by Dr. J.D. Bernal. Preface and Part 1. Introduction. This book is an attempt to record in my own words a set of lectures given in the term up to first-year students in physics at Birkbeck College on the history and nature of experimental physics. It aims to take physics up to the end of the period of classical physics, the end of the 19th century, just before the new discoveries of the atom and the general theory of relativity were made. This marked a change as great as, if not greater than, that which occurred in the Renaissance, and is called the First Scientific Revolution. In view of the prestige of the new discoveries, I felt it was likely that the older parts of the subject would be largely forgotten, and that something should be done in order to keep them in the minds of young physicists as a guide to the way physics has grown as a result of the interplay of necessities of navigation and gunnery on the one hand, and on the development of philosophical and religious ideas on the other. So much of modern physics is now deemed to be theoretical physics and to be achieved by complex mathematical techniques in which the role of the experiment is necessarily played down. This is a paradoxical situation, for at the present moment physical experimentation is more costly and elaborate than it has ever been in the past. I did not continue the lectures into this modern period, not because I was uninterested in that, but because I knew it was being dealt with in detail by the other lecturers in the Department of Physics in the college. Necessarily the historical element entered, but in a different way, because the men responsible for the great 20th century changes, such as Rutherford, Bohr, Planck, and Einstein, are only recently dead and are treated as contemporaries, so that there is no danger of their work being forgotten. In presenting a course of lectures verbatim on approximately so, it is impossible to give the resulting whole the same finished appearance as would be achieved in composing a written book. Apart from the curiosities of language in going from the spoken to the written word, much simplification had to be made in the historical narrative, and this has been presented without qualifications, but on the basis of historical studies, in which I have been long involved. See my books, Science and History and Science and Industry in the 19th Century. I have tried to make it clear that the opinions of the men of the distant past have a greater relevance than we usually realize. For instance, the idea of atom not only retains the language of the ancient Greek Democritus, who first postulated it, but there is also an absolutely unbroken connection between the atom of the Greeks and that of the modern physicist. Moreover, the ideas of the Greek philosophers such as Plato and Aristotle, fanciful as many of them are, also run through the whole course of development of physics from that time to this day. Much of the progress of physics has consisted in the criticism and overthrow of these ideas, however, so that even when wrong they have played an important part in promoting later knowledge. Not only the ideas, but also the techniques of physics have ancient roots. The experimental method itself is a human construction, inseparable from those of practical utility. Such developments as those of the common, or the cannon, or the steam engine are both products of the piston water pumps of antiquity, whether used for irrigation or for blowing organs. Originally, physics was a codification of the achievement of technologists. In the modern age, the process is reversed. Much of technology has become applied physics. Even such fundamental concepts as work and energy come from the field of practice. Even if the steam engine was rightly called a philosophical engine, depending on the understanding of the vacuum, it was at the same time made possible only by the practical ironmongers such as Newcomen and Dartmouth. I have thought that the historical method would be a very suitable introduction to the fundamental concepts of physics. I hope that those who read this book will be able through it to see something of the interplay between the theoretical and practical aspects of the subject. What is physics? These chapters are based on lectures given as a short introductory course aimed at explaining what experimental physics is and how it has come to be like that. I have been giving these lectures because I believe that it is useful to have some idea not only of what people believe now, which is after all only a temporary stage in the development of physics, but also how we came to think in that way and how the whole of current physics is tied up with its history. The very language of physics has grown up with the history of physics. This is linked on the one side with the development of practical devices, and on the other with the development of human thought in the philosophical field. We are too apt to think of science as something which exists as a group of bits of knowledge. It represents what we know, what we can use directly in practice, and further, is a basis for finding out other things. At present, science is all that and will be, I imagine, increasingly so in the future, but science is much more. It appears as a very rapidly moving river, and the most you can hope to do is to learn now, as it were, the course of the last part of the river together with some general clues as to where it is likely to flow in the future. You cannot predict what will happen, but you have to be ready to meet it, and that is why the teaching of science, particularly the teaching of physics, has to take this historical aspect very much into account. It is reckoned by actual analysis or references that the half-life of an average paper in physics is 2.5 years. That is, the chances are less than even of it being referred to after such an interval. If this were strictly so, of course, any benefit you received from a physics course would have vanished by the time you reached the end of it. But it is not quite as bad as that, for the papers refer to new knowledge, and even if the still newer knowledge catches up with that new knowledge, most of the old knowledge still remains satisfactory if it is properly interpreted. For instance, we will talk about atoms, but we would not like to say any longer, as did the Greeks or the Victorians, that an atom was eternal and unchangeable. The fact that an atom is not eternal and can change suddenly and violently is nowadays, unfortunately, only too familiar to us, but is still very useful to have atoms to talk about. In the same way, people could talk about men or cats before there was any anatomy or any knowledge of evolution. All the terms of the past and the methods of thinking about them are still useful. Most of what students do on the mathematical side of physics is to be found in Newton's Principia. The basic idea of dynamics, the equations of motion, the ideas of momentum, of inertia, of mass and acceleration, which were applied by Sir Isaac Newton to large bodies like the Earth or the Moon, or to the moderate-sized bodies like cannonballs, turned out to be very useful for handling minute hypothetical entities like atoms, or even smaller things like the fundamental particles that build them, or even things that we would say are not material at all, like the particles of light that we call photons. So the past still lives in physics, and it is worth seeing it in its contemporary pattern at the time when you are reading and learning to use it. The separation of the sciences. Now, with that slight introduction, I want to go straight on to considering physics as such, as different from other branches of science. How do we know, for convenience sake, distinguish physics from chemistry or mathematics? It used to be a much easier distinction to make. In fact, when modern science was growing up, from the time of Galileo Galilei to the time of Sir Isaac Newton, all the sciences were very much joined together. A single man like Hooke could do absolutely first-class research in pure mathematics, in physics, in chemistry, and even in biology. Towards the end of that time, however, the sciences were just beginning to separate, and after that, they continued to separate more and more. By the 19th century, however, in fact up to the time that I was in Cambridge, nearly 40 years ago, the science faculties were almost completely separate, but there were already signs that they were coming together again. Just at this moment, we are witnessing a great convergence of all the sciences. In order to be a good biologist now, for instance, you have to have a knowledge not only what might be called school physics, but quite a lot of really modern physics, quantum physics, and so forth, and a great deal of chemistry as a basis for biochemistry. Conversely, the physicist himself, even if biology is not a part of his subject, is, however, obliged to know something of it, because he or she may find a great deal of their work being concerned with biophysics. The problem for a physicist, rather than for physics as a subject, arises because physics is increasingly penetrating all the other parts of science. This is already evident in the names of the new hybrid subjects. Again, biophysics, and for example. So now we have a subject called chemical physics, which is different not so much in the proportion of physics and chemistry that come into it, as in its central interest of helping chemistry in the first case and of extending the range of physics in the second. Now we also have biophysics and biochemistry. It would appear that physics is spreading towards biology on one side, while on the other, the mathematical aspect of physics is also becoming much more marked, especially now that we have a growing symbiosis between physics and mathematics in computers. For the computer contains both the purely physical element in its actual components and mathematical logic in their arrangement. To develop and make the transistors or magnetic memory elements, or the newer devices that will replace them, needs a great deal of physics, but although the connections between the computers are actually made with material wires or printed circuits, their layout and setup are really pure mathematics. Again, this book was written in the late 70s. However, the history of physics, or classical physics, has not changed much since that time. The nature of physics. Well, what I am saying, first of all, then, before I try to define physics, is how difficult it is to define. Nevertheless, we can always fall back on this. And it is a very convenient thing to say. Physics is a limited subject. For examination of purposes, physics is heat, light, sound, electricity, and magnetism, with a small allowance of atomic physics. Here we will look more closely at the examination of purposes and at how such physics came into being. The reason why we can block out this particular part of knowledge and experience and call it physics is because it deals primarily with what might be called the extension of the human sensory motor arrangement. A man may be deprived of everything, deprived of tools or clothes, in the definition of a poor man. He is body only, yet he possesses a more complete set of physical apparatus in the shape of sense organs to register the external world and muscular effectors to change it. It is true that he also possesses an even more elaborate chemical apparatus for digestion and the maintenance of metabolism, but while the latter, metabolism, became intelligible very recently, and then only partially by sophisticated biochemistry, the physical sensory muscular apparatus is comparatively understandable, or at least it was there that man's rational understanding of his world, which we call physics, began. To combine sensory and motor experience, we must begin with sight. We use the word see very much as a form of understanding. You say, I see it, meaning that you see the connection. You see. You understand. Actually, sight comes very late in animal development. The earliest animals did not see very much. They worked largely on smell, which is a much more delicate, much more sensitive, much more varied way of sensing the environment, but is essentially chemical and not physical. Now, you cannot argue about smells. You cannot deduce anything from them at all. It is all subtle discrimination, memory, and association. But you can't argue about sight. You can say this is near or that is far. You can say this is on one side and not on the other side. You can relate sight to motion. One of the very big achievements in practical physics, yet a definitively pre-human one, is throwing something, especially throwing something at a mark and hitting it. Another very similar sort of achievement is projecting yourself in a free jump. Early animals, for a very long time, right back to their first coming out of the sea, managed to walk just by putting one leg in front of the other, and had built-in mechanisms for doing so in order. But jumping is a different matter. Fleas or sandhoppers just jump, and it does not matter very much where they come down. But to jump like a monkey, or a primate like we can, that can take a 20-foot jump and grasp a branch and hang on to it, needs a very much higher degree of eye-hand coordination, which is really the physiological basis of physics. A further stage in really human evolution came when a man not only threw a stick around but used it. He used it for poking something, for digging something up, or bashing something, like the other primates do, like chimpanzees. The use of a piece of wood or a stone is first of all an extension of the human frame, limbs and sense organs together. The naked man with his hands and teeth can do a certain amount. Armed with a stick and a stone, he can do far more. Human sight. The physical extension of man's awareness and activity came first on the muscular effector side rather than on the sensory side. Mirrors and lenses came far later than tools. Nevertheless, for understanding the world, the senses, even unaided, could go very far. This is especially true of sight. This is because, in particular, human sight is as much in the brain as in the eye. In the course of evolution, the brain came to have a built-in analyzer of the images presented on the retina of the eye. It is this analyzer that turns mere variegated and moving patches of color into a world of objects that can be distinguished and manipulated. In fact, we see things dynamically rather than statically. If by an ingenious device the eye can be kept fixed on any particular object, it cannot see it at all. The eye cannot detect light. The eye can only detect changes of illumination. The eye is always wandering around, as it were, monitoring the experience of the outside world. Seeing is not a passive perception. It is, in fact, an act. The ancients had indeed always thought it was an act. For a long time, they considered that you saw things by projecting something out of your eye. An eye beam. It catches the thing and brings it back to you, and that is how you see it. Consequently, of course, your eye becomes a very powerful magical instrument. If it is the wrong kind of eye, it can do all kinds of damage to the person it looks at. These were, in a sense, ancient rationalizations of what we now know as the act of seeing, and that leads immediately to the question of movement. Muscular movement and muscular sense is a part of our sensation, part of the action. We have always talked about the 5 senses, but there are more, like 7 senses, and one of the senses is the muscular sense itself. We have built into our muscles a very complicated set of strain gauges to measure the degree of pull they are exerting. Inside the muscle there are certain little organs called spindle fibers that have their own nerve quite separate from the one that works the muscle. And this tells us how tight the muscle is at any given time. Again, this is anatomy and physiology, but for even when we are not moving our limbs, we are sending messages to all our muscles. The limbs are very carefully balanced so that the muscles which are arranged in pairs, like the flexors and extensors, are exactly and actively balanced in what is called tone, muscle tone. That is how you can gauge, for instance, without moving at all, the weight of something in your hand. More orders have to be given to the muscles that are pulling up than to those that are slackening off, so as to keep the hand steady, and the difference of sensation in the spindle fibers of these 2 sets of fibers gives the weight. The old mechanics of the 5 powers was only a further sophistication of the body's ways of lifting things by lever, pulley, windlass, plane, or screw. We shall see later how by the use of these simple and extremely useful devices, a quantitative mechanics could be built up, man-powered in the first place. The first step towards this is the study of the lever as a balance. Balance in itself is built into the human frame. We need it more than most animals because we walk top-heavy on 2 feet and have to learn in infancy how to keep our balance, for which we are furnished with a leveling compass in our ears.